Okay, I'm glad to be here. I think we were one of the first customers of the Quantemol N code, and when Jonathan was trying to make it idiot-proof, we were actually the model for the idiot because we were probably the first non-collisional users of the collisional code. And I'll try to actually, let me start the presentation. Defend the stand of swarm physics. I had a feeling here that everything is hunky-dory. We have binary collision data, we have plasma modeling, and we can just jump from one to the other directly, and everything will work out fine. I don't think so, and I will try to explain why. I think that there should be a step in between which should be considered, and at some stage there were many swarm physicists, but I think I'm the only one left now. No, I'm not. Actually, most of them are now doing plasma physics, and there are several in the audience, but actually word swarm is used more and more often, and there are fewer and fewer people who would say that they're doing swarm physics. Anyway, so when the title of the talk is Actual Conversation That Took Place. I used it once to make a joke at the beginning of the presentation. This is actual conversation when I try to explain what swarms are to a young, very good-looking, binary collision female scientist, exact opposite of me, and very smart, exact opposite of me, as I said. She immediately said, "Oh, do you mean that your beam is really, really lousy?" And I had to think of an answer, and I said, "And when you say beam, do you want to say that your energy distribution function is really, really unrealistic?" And this is the seesaw between the swarm analysis and the binary collision data, and I will return to this on more than one occasion during my... Okay, and how we apply all that? Well, basically, as I said at the beginning, there is a feeling that you could come from the top to the bottom in one step, and I will try to explain to you why actually I think that you should also make all these measurements and tests and do the swarm data analysis. What are swarms? Well, if you take this degree of ionization line, swarms are in the left corner where the collisions dominate and there are no space charge effects. When you have I had very often reports from the referees, and most of the low temperature plasma people got from fusion people, apologies to fusion people, when they say that, but these are not real plasmas. Actually, name plasma was given based on glow discharge, which is somewhere almost on the boundary with swarms. So these are the real plasmas. And in those real plasmas, basically you don't care what the gas is inside. Coulomb collisions dominate everything, and you have all these nonlinear phenomena and you play with them, and that's fine. At the other corner, however, you can neglect Coulomb collisions and you have to look at electron-molecule collisions, but the advantage is that you can control electron kinetics separately from the kinetics of ions, so you can make a very non-equilibrium system where your room temperature gas can feel fine against your skin when you do plasma medical application, and you can at the same time dissociate molecules and produce active species that would do something useful. So, of course, you have to match them both to study all sorts of discharges, and we had discussion in previous lecture on degrees of ionization and how they affect the plasma. Okay? So basically, and I'm repeating myself now, swarms are ensembles of charged particles which move through the gas through pristine gas that was not affected by their presence and they're only influenced by collisions and by external field. Okay. And swarm analysis is basically bookkeeping. Chartered accountancy, as you would say in Britain. You just have to match, and Liam mentioned it, balances of everything. And it's not really, as Monty Pythons would say, lion tamer kind of thing, but you have to match all the books in the end. And I will make a case for a more specific matching of the books later. You have to match it locally at every energy point, not just globally overall. Basis of swarm are experiments which were built to take advantage of very low electron density. So actually, in this Cavalieri diffusion experiment, we were able to record a single electron and make experiment with a single electron. I have no time to explain those experiments, but you can measure diffusion coefficients, and each of these has a nice story, and most of them were built by Bob Crompton and made them to be very, 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 very accurate. Unfortunately, he retired, and there are museum displays in his laboratory. So we take swarm data, put them in a database, and basically we should dream up a cross-section and calculate the transport coefficients and compare with experimental data. Of course, unless you put the input from what's available, you can run around chasing your tail for many, 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 many iterations and get a lousy set of results. So basically, you need as much help as you can get, and you should match all these approaches into a single unified approach. Once you run through this system and calculated and measured data agree, you can only say that your set of cross-sections is consistent with the collisional data because this is not a direct procedure to get the results. Now, the advantages of this approach were more important in, let's say, 20, 30 years ago, when you could get absolute cross-sections without worrying about pressure calibration, matching beam densities, beam profiles, and things like that. At the moment, experimental techniques are binary experimental techniques are getting better and better, but I haven't seen a single theoretical approach or experimental technique that can do everything. And if you put different sources of data into the same set, even though they may be the best in their own right, there could be some mismatch, and you can end up with really wrong distribution function. Of course, limitations of swarm technique are advantages of binary collision technique. It's indirect, there is non-uniqueness problem, and there is averaging over many important quantities, but to plasma modeling, that's okay. Okay? I'll show you some examples. High accuracy. Well, these are two sets of drift velocities from Art Phelps and just a little improved set from Bob Crompton, and you can see how different the resulting cross-sections are. But the most accurate cross-section that was obtained in this procedure by the most accurate drift velocities actually produced momentum transfer for helium, which turned out to be matched to better than 0.5% by every other calculation later on. And actually, there is a story that at some conference, some well-known, well, I know the name, professor came up with a resonance in helium at 4 or 5 electron volts, and Bob Crompton made a phone call to Canberra, and during the conference he was able to say, no, there is no resonance there. Yes, there is no resolution, but you can give overall balances and you can test Of course, there are problems, and well-documented problem, and I know exactly when it started. It was when I was doing my PhD thesis, and one binary collision gentleman and one swarm gentleman wanted to match the two techniques and prove to the world that we are now all happy and we can proceed on to brighter future. And I was supposed to compare the results and could never really match Michael Morrison's calculations with Bob Crompton's previous swarm measurements. The cross sections were quite different. This is the swarm result, and blue are theoretical results by Michael Morrison. And few years later, actually, in Crompton's laboratory, Steve Bachman did beam experiments and put a nail in swarm's coffin, or so they say. I'm still not really convinced, absolutely, that this is the final on this problem, because if you look at nitrogen, there the beam and swarm results agree, and the same theory by Michael Morrison disagrees by a factor of 2. So what is going on, and why vibrational excitation? And I don't think that we have full resolution of this at this stage, though there were many attempts and there were many claims that it has been done. That example is NO. We were able to get this type of cross-section from swarm study. Don't ask me how we get all this energy resolution. Of course, we had input, and the input came from beam measurements. When we looked at the peaks, we looked at the profiles of resonances, and we matched them by assuming that there are 2 or 3 resonances, but actually 2 resonances were enough. And we were able to actually prove that Schultz's data are by a factor of 40 too small. Luckily for us, if you use Schultz and put calculation of d over mu, your d over mu is way out, almost a factor of 10. So mean energy of electrons would be too large. And luckily for us, Tom Resigno's group and Bachman's experimental results, and also Michael Allen. Actually, Michael Allen's data sit on top of our data almost perfectly, agreed with us. So we were able to show that actually by looking at swarm data and using input from binary collision data, you can get a fairly good results. And my suggestion is that actually a joint approach is the best way to go. Okay, well, I couldn't find my closing argument, so I'll just close it with something that we got from the local group and their collaboration with Nigel and their calculations of cross-sections for radicals, where basically you cannot do swarm experiment, but if your electrons cool down from 4 or 5 eV down to parts of eV or to room temperature, you will have a large increase of attachment to radicals, and that could, under some circumstances, explain some of the observed increases of attachment in the afterglow. Thank you.